Hello, now we are going to start with the new part that is related to some case study and is specific to the advanced systems engineering approaches, that how the systems engineering approaches could be deal in the research and the real world at the advanced level. So first we'll see the approach for the stable network evolution rule mining for system stability and changeability analysis. So this work was been published by me and my co-authors at IEEE Transaction on Emerging Topics in Computational Intelligence and 48th IEEE International Conference on System Nance and Cybernetics. So in this, we'll see evolution rules, stability, changeability, rule mining, changeability mining, SNS properties, and then the experiments. So first of all, to understand this, we need to understand what is sequential rule mining. So basically, sequential rule mining is a kind of association rule mining. And what is sequential rules are being defined? They are defined like if some event occurs, then some other event will also likely to be occurring, and with a given probability and some confidence. So you can predict the future based upon the known past. It means that if X appears, then Y is legally likely to be appearing with some given confidence. To the rules of such kind, sequential rules and association rules are having support and confidence. What are the examples of sequential rules or association rules? So this sequential rules is like Vivaldi, Mortaz, and Handel, and Berlioz. These are the type of music. So if the customer has bought music of me, these are the singers or some lyrics person. So if the person is purchased the music of Vivaldi, Mortaz, or and Handel, so in that order, then most probably Berlioz Berlioz will be the music of the Berlioz will be purchased by the same customer or the number of customers who had purchased this antecedent. They will most probably purchase this consequent, means this will be purchased by those customers as well. So this is how the database look like. Means this is a small example of six transactions. So six sequential data items are like this. So the sequence is important in this sequential rule mining. And the for example, if you want to calculate the support of Vivaldi, Handel, and Berlioz, so the support will be 50%. Means one, second, and fourth sequence actually contains these three items together. And Vivaldi, Mortaz, and Handel will actually most probably infer that the Berlioz will also be purchased out. Means with a given support of 33%, because this sequence was occurring, all these four were occurring in one sequence one and sequence four. So we can see Vivaldi, Mortaz, Handel, and Berlioz. And in this also, in the fourth one also, it is occurring. So we can see this one and this one. So this will actually give this support. Then what is the confidence we can say? We can see confidence based upon the how many times that this occurs. This occurs means this occurs at 50% at this and followed by this. So what is the times that it was being followed? So it will be followed by all the times. Means this sequence will be like this every time. So this will give us 100% confidence. Means it will be like this will be 1 divided by 1 multiplied by 100. So it's like 2 divided by 2. So it's 2 divided by 2. So 2 divided by 2 multiplied by 100 equals to 100%. Then next, we'll see the definition that we provided, that how rigorously in our research we had defined the definition for X drives Y to define evolution rules or stable rules. So X drive Y for the data set DI, means database, that will have the some states, and this database series is defined as D1, D2 up to the DN for some state series SS. And then the rule will be interesting in SI, means any state SI, if its support and confidence is exceeding the given threshold. Then what is the distinct rule that occurs in the multiple states? That in the basis of that, those distinct rules are said to be evolution rule, and they have the given stability in a state series. Then wherever the stability is, means we can define the stability as the percentage of the occurrence of them as interesting. Then evolution rules are basically stable if they have stability exceeding the given threshold, that is minimum stability. Then we can say the stable evolution rule as the stable rule. Thereafter, system network database SysNetDB is being made up of these connection pairs CP1, CP2 to CPN, and the M is the total number of connection pair. Then SysNetDB means system network DB is being defined, and so this for a particular state. So multiple SysNet DBs could be denoted as sysnet DBs, means this is the set of series of system network databases, and ith will represent the state SI. So this is sysnet DB I representing state SI. Then new network rules are being defined like the state that SI that can be expressed as X drives Y, where X is the subset of source entities, that is SSI. Y is a subset of the target entities. So this is how we define the network rules. And then the network evolution rule is defined over state series. That is again expressed in the form of X drives Y, that X is the subset of source entities SS, then Y is a subset of the target entities, that is TSS. You can read the research paper for getting the detail about this. And then the NER has the characteristics stability because it is distinct and interesting in one or more uh, states. Again, we define the stability count like X drives Y have the stability count in that state series such that it will be having n. N is the stability count where n is the number of states in which this rule X drives Y is interesting and said to be NER. Then the stability is being defined as the stability count divided by cardinality. The cardinality is the number of states in a state series. Then NER is X drives Y, which is defined as stable in the uh, with its stability because that stability is greater than the minimum stability count, and such NERs are being defined as stable network evolution rules. Then we formulated two formulas: stability matrix SM, which is having minimum stability multiplied by number of stable rules divided by number of evolution rules multiplied by 100. Then system network could be defined as system network stability matrix SNS matrix with minimum stability cross SNER count divided by SNER count multiplied by 100. Then the changeability matrix CM could be defined as n divided by minimum stability count cross NER count divided by SNER count multiplied by 100. So this is stability matrix and changeability matrix, where n is the number of states that we know, and minimum stability count is the threshold that we'll get during the SNER mining. And an NER count is basically the number of NER retrieved, and SNER count is basically number of the SNER retrieved. Then what is the value of n divided by minimum stability count? It is actually a reverse of 1 by minimum stability. So it is inverse of stability. Then next, so we'll see the illustrative example. Suppose you have a state Si which could have the this type of graph, and this graph contains E1, E2, E3, E4, E5 entities, and they could be represented as 1, 2, 3 in the connection pair 1, connection pair 2, connection pair 3. So this is sysnet db for ith state, for this state. And then you actually do the minimum s- support and minimum confidence for doing the network rule mining, and you will generate some network rules because this is a network database. And based upon this you can even further calculate the sysnet SNS matrix, and we'll see it later that how we can calculate it. So this this is three connection pairs: connection pair 1, connection pair 2, connection pair 3. And you can have this output of network rule mining based upon simple notion of that minimum stability and minimum uh, confidence. Then you can have this collection of network rule generation. So you have generated the collection of network rules such that you have various rules, and you just find out what is the number of occurrences of these rules, and based upon that number of occurrences you can tell that these are basically stable, these are not stable. So if something is stable, that means that it is occurring more number of times, and if it is occurring more number of times, then it means that it is stable. At, for example, this is occurring three times. One drive four is occurring three times. One drive, two drive, four is occurring three times. So all the rules that is occurring three times are stable as compared to other rules. So these stable rules will actually form stable network evolution rule defined over here. And this actually rule as the interesting with its support and confidence, that we can have greater than minimum support and its confidence. Then the stable rule, if the stability count is greater than the minimum stability count, and we can define the experiment as 2 0.5 comma 2, and you can calculate the SNS matrix, means stability matrix, with equation 4 that we had seen over here. So you just put the values that 2 is the 2 is the that number of that states, and the minimum support count. So 2 divided by 3 means a number of states, like over here this minimum stability over here. Min stab is basically minimum stability count means 2 divided by 3. So it is 2 divided by 3. Minimum stability count is this means stability percentage we want to calculate. So minimum stability is 2 divided by 3, means number of the states in which it is stable, and then divided by the number of uh, then you have the 5 divided by 11. So this 2 will be the minimum stability count, that is 2 divided by 3 is the number of states, then multiplied by 5 divided by 11. 5 is the number of these selected stable rules, stable network evolution rule, divided by 11 are the whole set of collection of network rules. So it will give 30.3 percentage of stability. Then you can have real-time experiment like this same thing. So these are the basically entities or words in the multi-sports event uh, network or some database, and you can create three database out of 1890s, 1990s, 1910. So these are the connection pairs, and these type of data network are being created. This is just ID representation of them. Then you do the network rule mining and generating the network rules for the support confidence and the support count and some confidence. Then thereafter you do the network rules generation for support count and confidence by this. And similarly for the database 3, you can generate again the output for the network rule mining. And thereafter you can do the collective 37 network rules were being generated out of this three states, and 36 uh, are the network evolution rule, unique network evolution rule, and one of them was being selected as stable network evolution rule, and the stability minimum stability was being used as 2, and thus it will be two states out of three. So you can say that 3 divided by 2 for calculating changeability matrix, 3 divided by 2 cross 36 divided by 1 cross 100. So that's the same formula for the changeability matrix, n divided by min step count, NER count, and SNER count. So this is total NER. This is one is SNER, three is the number of states, and two is the minimum stability, and you'll get this type of mm, result for the changeability matrix. And you will have this as the stable network evolution rule. 2 drives 5. What is 2 drives 5? So 2 is games and 5 is basically regional. So games drive 5 means game, if game would occur in the keyword, then regional would also occur. Then this approach could be formulated like the n states was being chosen from the evolving system to make a state series like this, and then the n states are being pre-processed to generate the n evolving network, and these n evolving networks are being used for creation of system network databases. Then system network databases are used for doing the network rule mining, and this network rules are being generated, and this network rules are being generated, and you can have this and you just merge them and generate the network evolution rules. And these network evolution rules are being mined to calculate the which are having the more stability as compared to minimum stability threshold. So the stable network evolution rules are being generated, and then you use the minimum step as and n count for the NERs and SNERs to calculate the changeability matrix. So this is the flow chart for the same thing, and you calculate the stability matrix, NERs, SNERs, and the whole thing. So this S1, S2, and up to the Sn are the n states are being chosen, and you do the pre-processing, and you do the pre-processing, then you generate the n evolving network, and you generate the thereafter further pre-processing you do to generate the system network database generation. So for state one, sysnat db1, sysnat db2 for second state, so on. Then you do the network rule mining, generating the network rules for n state. Then you do the collection of network rules of n state. Then you do the distinct analysis for the network rules and calculate the stability for them. And then you say it as the network evolution rules, and you form the entity ID and their stability. Thereafter, you calculate the mm, stability of those NERs. If the stability of those NER is greater than min step, then you can say it as stable. So it will be set as a stable network evolution rule. And then this will be the whole part of mining NERs and SNERs. And then you can use this information for calculation of stability matrix. Then this algorithm was being denoted like this. So the whole thing initialization step is this, and you calculate network rules from this algorithm, and this was the initialization of data structure. And then you use the stability for the network rules, and then you do the collection and burning of the all data, all the network rules. Thereafter you do the simple that NER calculation, that collection of the network rules, and then you do the uh, thresholding. If and first you calculate the stability count. What is the stability count for each NER, and based upon the stability count, if the stability count is greater than minimum stability count, then you define that NER as SNER. So you add this NER as SNERs in the database. Thereafter, you put output uh, these NERs and SNERs and changeability matrix. What is changeability matrix? So NER count uh, divided by SNER count and the N state number of states that we are using for this data structure. Then the minimum stability count, and then CM was being calculated, and CM was computed and stored. Then next, you have the this type of experiment was being done that Hadoop SDFS core libraries, 15 libraries are being used, and they have the 3,129 entities, means procedures. This type of experiment was being done for minimum support to minimum confidence and minimum stability count. And NERs was being retrieved and stable network evolution rules are being retrieved. Thereafter, you get these type of this much number of target source entity and target entity and source entity. We calculated the changeability matrix over it. Then you get, we also applied it for the list of Bible translation, list of multi-sports event. For the 13 different, uh, for this Bible translation was being done for the 13 different centuries, and multi-sports event was being done for the 13 different decades. So the analysis contains this number of words in them, and this was the experimentation parameters. And then this NER's calculation, stable network rules ca- count calculation, number of entities calculation, and changeability. And retail, similarly, we did for the retail market analysis that 13 months are of the data was being used, and we did the generation of number of entities generation like this. And this was the experimental parameters, number of NERs generation, number of stable rule generation, then what is the number of source and target entities, changeability matrix, then positive sentiment and of the movie genre and negative sentiments of the movie genres are being generated like this. Thereafter, we did for the 16 different decades of IMDb dataset. So there are these type number of entities were being used for positive and negative sentiment words. So and then this type of uh, experiment was being done. Thereafter, we generated this much network evolution rules and this stable network evolution rules with this much source and target entities in stable network evolution rule count. And this was being calculated as changeability matrix. Then these are the examples of rules like in the Hadoop SDFS create procedure occurs, then most probably convert will procedure will also occur. Similarly, if the Asian Games occurs, then most probably regional would also occur in the name of multi-sports event. Then in the positive sentiment, if premier would occur, then it most probably belongs to short genre. Grand will occur, then most probably it belongs to the music genre. Thereafter, we can see the Bible translation. So English and English and modern English was mostly being translated to the from Vulgate, Masoretic, and the Greek text. So modern English Bibles are mostly being translated from Vulgate, Masoretic, and Greek text. Then this customer 17841 would actually purchasing these much uh, items, these much products for the many months together. So we can analyze this customer very well, very easily. Then if Ryu, terrible, pain, vent, passe will occur, then most probably it belongs to the short genre. Whereas Ryu will denoting the documentary kind of movie. Brat terror would occur the drama and horror type of movie. So this type of vocabulary could be used for analyzing what is the genre of the movie. So this is showing that the advantage of generating SNER over NER. So SNERs are lesser in number, which actually gives more chance for us to analyze. So this will give even more information that these are the large number of NERs, whereas there are less number of SNERs are this large number of NERs, less number of NERs, SNERs. So large number of NERs, less number of SNERs. So it's easy to analyze less number of SNERs as compared to large number of NERs. So large number of NERs are less interesting, but the less number of better stable network evolution rules are actually more interesting as compared to this one. Then you can have this type of data result as well. So this is less interesting 131. This is more interesting 25 SNERs for frequent market basket. Then we can have the positive sentiment and negative sentiment. So more number of NERs, less number of more interesting SNERs, more stable SNERs. So less number of means more interesting and stable SNERs for both positive and negative sentiment. So this is like the nine data set, nine experiments that we did that were be mentioned in this table. So this is the experimentation points to 4 dash 0.6 dash 5 for the minimum support count, minimum confidence, minimum stability count. So these are the nine experiments for the different six different evolving system: Hadoop, HDFS, multi-sports event, Bible translation, retail market, positive and negative sentiment. So 9 points for them, and this will actually having the system network SNS system network stability matrix. So this is how we calculated this information, and then we further devised all the minimum stability fractions over here, minimum stability count over here, then number of states, then SNERs count, total NER count, stable network evolution fractions over here, SNS matrix calculation, and this type of information was being calculated for six different evolving system that we had studied. Hadoop as a software system for software evolution analytics, Bible translation, multi-sports event for natural language evolution analytics, retail market for the market basket evolution analysis, then positive and negative sentiments for the IMDb movie genre negative positive sentiment analysis. Then the conclusion for this approach or this work was like that it introduced stability as the new measure for analyzing the network evolution rules. Then we defined stability as the percentage of the states in a state series where this NER is interesting. Then we also defined like the NER as stable in the state series if the stability of that NER exceeds the given threshold of minimum stability. Then thereafter, we defined an algorithm for doing the SNER mining and changeability matrix as the SNER, NER, and you have the this set of states for doing the evolving system analysis. Then the purpose of this SNER is to compute the changeability properties, and this SNER and change mining algorithm was being proposed as an intelligent tool, which was being used to do the experiment and summarize the result for the SNERs, and we have chosen the minimum support and minimum confidence for this type of and minimum stability count to do the experiment. Then thanks. Next we'll see system network complexity. I hope that you enjoyed this rule mining, network evolution rule mining part for system evolution analytics.